Hello everyone and welcome to today's lecture. Today we'll be talking about various properties that are useful when computing integrals, double integrals. We'll also talk about certain applications and theorems that extend from single variable calculus to multivariable calculus, which are very useful as well, such as the mean value theorem, and then also the idea of solving for, say, a given value by using, such as volume or area of a function, using the double integral. And we've already seen this for rectangular domains, but we'll see that we can even set up double integrals for non-rectangular domains as well. So let's start off by listing some of the four basic properties that we can always apply when integrating. And we'll just remember here that for each one of these properties we'll be talking about, say, the integral of one and possibly two functions. So we'll have two functions, f of xy and g of xy, of two variables that are integrable, or Riemann integrable, so we can do the Riemann integral of both of f and g. And we'll be integrating over a domain, we'll call it R. In two-dimensional space. So we'll be considering properties of the double integral over some region R. So the first property, and a property that we saw in some of the examples gone over in the previous lecture, is that what happens when you take the double integral of any constant c. So suppose c is a constant real number, and we take the double integral over the region R of a function f of xy dA. This is the same thing as that constant c times the double integral of f. So we can pull constants out of the integration process, just like we can in single variable calculus. The idea behind this is very, very, if you want to say prove this or show this, we'll do a justification. Well, the Riemann sum for this function, c times f of xy, is just going to be of the form, it'll be a summation from, double summation from I equals 1 to n, and then j equals 1 to n, of c times the sample point, so c times the function at the sample point, times delta aij. And because this is a summation of multiple different values, from the summation rules from a previous calculus course, and also you can think of just, algebraically, if you do c times a plus c times b, this will always be equal to c times a plus b for any finite sum. So this sum is going to be the same thing as c times the double summation over I and j of the function at the sample point times delta aij, which is the Riemann sum for the integral of the function f. This is a nice justification of why the constant rule holds. So this tells us directly then that the constant rule is telling us that if you take the integral of any constant times a function, it's the same thing as that constant times that double integral. We have the sum and difference rules, which are also very, very similar. It says that we take the double integral over some region R of f of x, y plus or minus some function g of x, y. The sum difference rules tell us that this improper integral, or this integral, is going to be the same thing as the sum or difference of the first function with the second function, the integral of the second function. This is both over R. This is very, very useful. It says that if you have two functions, the sum or difference of a number of different functions, you can actually just consider each one individually and do each one individually. So again, this rule is very, very similar to the rule for single variable integrals. Not only that, the justification again is similar. I won't go through the justification for every one of these, but I can assure you that all of these justifications are done using Riemann sums, very similar to how we did the first justification for each of these properties. This is the second major property for integrals. The next property is called the domination property. And this says that if a function, say f, is always greater than or equal to another function for points in the region R, then necessarily the double integral of the top function must also be greater than or equal to the bottom function. For points in R. And this also kind of gives us a justification before for saying that, well, if a function is positive, so greater than or equal to 0, then the double integral of that function will also be positive over the region R. But you can double integral of it, and it shows you that that exact value can be thought of as a volume. It's the exact volume under the graph of the function f of x, y, which is very cool. And the last property that we have, again, all of these properties are directly from analogous properties for 1D functions, but they also hold for multivariable functions as well, which is nice. So the final property is called AddActivity. And this says that if our domain R can be split up into multiple different parts, which any domain can, let's say we have our domain R, and this is, say, split up into two separate subdomains, R1 and R2. The additivity property says that the double integral of the function over R is in fact equal to the double integral of the function over R1 plus the double integral of the function over R2. This is analogous to how in 1D calculus, in single variable calculus, for any interval from A to B, if you split it up into a two parts, or any number of parts really, and you integrate the function from A to B, the integral from a to b of the function is the integral from a to c of the function plus the integral from c to b of the function. Right, so that's what this additivity property is saying. It's directly generalizing this property, the additivity property for single variable integrals. But it's very, very powerful for us because what it allows us to do is take very complicated domains and just compute the double integral over those domains by adding the double integral over simpler pieces and simpler portions of the domain. So these are the four basic properties that we have for the double integral, and it really helps us go through and calculate the double integral on any domain we wish to consider. So I would call these the most basic properties of the double integral because they're used most frequently in terms of going through and simplifying calculation procedures for the double integral. So we'll look at some more advanced properties now as well. And in order to do that, we first need to go through and define what it means to take the average value of a function, because this is going to be intimately related with what's called the mean value theorem for double integrals. So you'll hopefully recall that in 1D, for a single variable function, the average value of a function is defined as follows. If you have a function on some interval from a to b, and we define the average value of the function on that interval to be the accumulation of the function on the interval divided by the size of the interval. And so both of these things can be calculated directly. The accumulation of the function on the interval is the integral, definite integral from a to b of the function on the interval. And the size of the interval is just the length of the interval, or b minus a. So this is the main formula that we have for the average value of a function. Computing this value will give you a number, and that number is exactly the average value of the function on that interval. Using this idea, we can go through and prove, using the fundamental theorem of calculus, what's called the mean value theorem. Which states that for a continuous function on an open interval, that there exists for a continuous function f, there exists a point, at least one point, I'll put in parentheses possibly more, for which the value of the function is equal to the average value of the function. So let's say we have that point. You can go through and solve for that point if you have the average value, and we'll say that, so this means that, say, so we'll call this point xi. So this means that at this point, the value of the function at xi is equal to the average value of the function, or the integral or accumulation of the function divided by the size of the interval. We can rewrite this a little bit by saying this is the same equation as saying that at this point, the integral of the function from a to b is equal to f of xi, which is that special point, times b minus a. Okay, so this is guaranteed for us that there exists some point xi that satisfies this equation. Going through and solving for xi sometimes is a tricky procedure, but we're guaranteed the existence of this point from the mean value theorem. And so what that means then is that we can actually always bound the integral from a to b. So if this is true, if this is equal to at some point the definite integral of the function, and we need a dx there as well to be consistent with our integral notation. So if at some point the integral from a to b of the function is equal to the function at some point times b minus a, well, that value of the function, f of xi, will always be bounded above and bounded below by the maximum value of the function over the interval from a to b, and it's bounded below by the minimum value of the function from a to b. So this improper integral then, or this not improper integral, this integral will always be bounded between the maximum value of the function on the interval from a to b times the length of the interval and the size of the interval, and it'll always be bounded below by the minimum value of the function on the interval from a to b times the length of the interval. So this is kind of a powerful result. It says that for any function, continuous function on any closed interval from a to b, we can always do this procedure and figure out what the total maximum is, the maximum possible value for the interval is, and what the minimum possible value for the integral is as well. We have an upper and lower bound, which is very, very useful in many, many applications. But the idea here is that this is kind of a review of the 1D mean value theorem and the 1D average value formula from single variable calculus, so a Calc 2 course. As it turns out, which is a very common theme in multivariable calculus, is this can be directly generalized to double integrals, and also we'll see to triple integrals a little bit down the line. So this idea of average value and the mean value theorem are directly extendable to functions of two variables for the double integral. So we'll go through and figure out first what the average value of a function of two variables is going to be. and then go through and state the mean value theorem for this. This is average value of a function f of xy on some region R. So just like in 2D, we have some function, and this function is, say, or just like in 1D, this function is defined over some region R. And let's say we want to find out what the average value of this function is on this region R. Well, this average value, again, we want to think of it as the accumulation, total accumulation of the function in the region R divided by the total size of the region R. Both of which we can actually evaluate, which is very, very nice, using the double integral. Specifically, the average value of f is going to be equal to the accumulation of the function is just the double integral of the function over the region R, and the size of a two-dimensional region is going to be the area of that region, or as we showed last lecture, just the double integral of the constant function 1 over that region. For rectangular regions, that area is relatively easy to calculate, but be careful because in general, for a general region R, we don't know that it's rectangular, so you might have to go through, when you're calculating the average value, in general, compute two integrals. You'll have to do an integral procedure for the numerator there, and the integral procedure for the denominator as well. So please be very careful when you're going through and doing that, right? Not all regions are rectangular. You have many different, more complicated regions. So this formula is more complicated if you have a more complicated region, which in general is true for the double integral and the triple integral. But using this idea, we can directly state the mean value theorem for functions of two variables. And it is very, very similar to the 1D case. It says that let f be a continuous function of two variables on some region R. This is saying, the mean value theorem directly is saying that there exists at least one point possibly more, such that the value of the function at the point is equal to the average value of the function over R. So we'll call this point for notation xi comma eta, which are two Greek values. So the x-coordinate is xi of this point, and the y-coordinate is eta. So what the mean value theorem is telling us is that the value of the function then at xi comma eta is equal to the average value of the function, or the double integral over r of the function, divided by the total area of the region R. So this is the same thing as saying, if you multiply by the double integral of the function 1, or the area of the region R, it's the same thing as saying that the double integral over R is equal to this f of xi eta multiplied by double integral over 1, or the area of the region R. And because this function f will always be bounded between its maximum and minimum values, so we'll call the maximum value of f m over r, and the minimum value lowercase m. This equation is telling us that the double integral of any function over any continuous function over any region R will always be bounded above and below by the maximum value of the function times the area of the region R, the double integral of 1, and it'll always be bounded below by the minimum of the function times the double integral of the constant function 1, or the area of the region. So this is the direct extension, right, of the mean value theorem for a single variable function, but it turns out that it also works for a multivariable function as well, and it's very, very important. It's a very general result. Proving it is not straightforward, takes a little bit of work, but the idea here is that it's directly applicable to many different scenarios that you might want to consider if you don't know how to evaluate an integral. So you can use this in a very powerful manner to figure out the correct bounds for an integral. So we'll consider the following example and show that we can directly do this and apply this theorem. Specifically, we'll consider applying this theorem to the function f of xy, which we'll take as the polynomial x cubed minus 3x minus 1 times y squared on the rectangular domain from -2 to 2 in x and -2 to 2 in y. And the first thing we have to do to apply the average value formula is to figure out the integral of this function on this region. So let's go through and do that. The double integral over r of this function is going to be the iterated integral from -2 to 2 of x cubed minus 3 times x minus 1 times y squared and this is evaluated by doing the inner iterated integral first. So the antiderivative of this function with respect to y is going to be x cubed times y minus 3 times x minus 1 times y cubed over 3, which is just x minus 1 times y cubed. This is evaluated from 2 to -2 from the fundamental theorem of calculus for single variable functions. this integral now, when we plug in, will be the integral from -2 to 2 of x cubed times 2 minus x minus 1 times 2 cubed minus x cubed times -2 minus x minus 1 times -2 cubed, which simplifies to the integral from -2 to 2 of 4 times x cubed minus 16 times x minus 1. This will be equal to the antiderivative of this function with respect to x, which will be x to the 4th, 4 times x to the 4th over 4, which is just x to the 4th, minus 16x squared over 2, which will be 8 times x squared, minus 16 times x times -1, which is plus 16 times x, evaluated from -2 to -2. So our final value will be 2 minus 8 times 2 squared plus 16 times 2 minus -2 to the 4th. Oh, and this should be 2 to the 4th right here because we're plugging into this guy right here. Minus 8 times -2 squared plus 16 times -2. And when we go through and simplify this, 2 to the 4th minus -2 to the 4th is 0. 16 times, well, we have this -8 times 2 squared minus -8 times -2 squared, which will be 0 as well. And then lastly we have 16 times 2 minus -16 times 2, which is going to be 16 times 4. So our final value for this integral is 64. So this, the integral of this function over the rectangular domain from -2 to -2 is exactly just equal to 64. Which means that the average value of this function on this interval is going to be the integral of the, on this domain is going to be the integral, double integral of the function over r, which we just calculated, divided by the area of r, or the double integral of the constant function 1. Now, this will always simplify down to just the area of a rectangle for rectangular domains only, but because we have a rectangular domain, we know that this is going to be exactly equal to 4 times 4. So the average value of this function is going to be the accumulation of the function, which we found before to be 64, divided by the area of the region, which I recommend going through and showing that it'll just be 4 times 4, but this will always be the case for a rectangular interval, that it's just the width of the base times the width of the height, times the length of the height. This is going to be 64 over 16, or 4. So the average value of this function of f on this domain we've calculated to be equal to 4. Now what this means is that the mean value theorem guarantees at least one point, possibly more, such that the value of the function at that point is equal to this average value. So any point that satisfies the value of the function equal to 4 is satisfying the mean value theorem. So what this is showing us is that, right, this is a lot of points. There's actually infinitely many points. Any points on the level curve of the function that correspond to the level 4, are satisfying the mean value theorem, because the value of the function at that point is equal to the mean value or average value of the function. This is best seen by visualization. So what we're going to do is show a level curve plot of this function and show exactly where this is for this function right here. So let's open up Desmos and do that. I already entered all of the Desmos functions in, so we can see this immediately when we open up this plot. So here you can see all of the level curves of this function, and I'll go through right now and explain the mean value theorem in its application here, and you can hopefully see this in this already. But so we'll go through and explain the level curve plots here. So this solid line right here, it's a black solid line, as well as this solid line right here, and this solid line right here correspond to the function being equal to 0. The dotted lines, the dotted curves I should say, correspond to negative values of the functions. This is -1, -2, -3, and so on and so forth. Same thing right here and right here as well for these dotted lines. So those correspond to negative values of the function. The other solid lines, which are red, correspond to positive values of the function. So this line right here, or this curve right here, corresponds to the value of 1. This one corresponds to the value of 2. This one corresponds to the value of 3, and so on and so forth. So the function's increasing in this direction, increasing in this direction, increasing in this direction, decreasing in this direction, decreasing in this direction, and decreasing in this direction. The last line that's of interest is the dashed line, which is a green line. And that line is the level curve of this function corresponding to the value of the function being equal to 4. And what we've shown is that this any point on this line is the function value is equal to the average value of the function on this domain, which is satisfying the mean value theorem. Because any point here on this curve, the dashed curve, is satisfying that its function value at that point is 4, which is the average value of the function. Therefore, it satisfies the mean value theorem. And you can kind of see that it's kind of in between, the average of this function. It makes sense that it's 4 because there's definitely more regions here where you have a more positive value of your function than a negative value of the function. This is a very nice example showing directly, the application of the mean value theorem to an actual example function. So for the last two examples, I want to go over how to actually go through, and these are going to be general examples of integrating over non-rectangular regions. So we've seen a number of different rectangular region integrals, and now we want to do the double integral over non-rectangular regions. And the way that I'm going to introduce this is through a problem that hopefully everyone knows the answer to, and that's the problem of exactly showing, maybe you don't know the actual proof, but that you probably know the answer to it, which is, what is the area of a circle? And the second question is the more interesting question: how do we get that formula for the area of the circle? And hopefully you've seen already once, maybe at some point, in a relatively lower geometry class, you might have memorized that the area of a circle is exactly pi times the radius of the circle squared. Well, it turns out that using our definition of area from the double integral, we can directly go through and actually derive this exactly. So we'll draw a picture first just to ground ourselves. And the idea is that you can immediately see that when you draw a circle, this is definitely a non-rectangular region, because of that the function in the top and the function in the bottom, right, are not rectangles. So if our circle has a radius of r, then we want to be able to go through and figure out what the area of this region is. So you'll recall from before that we defined the area of any region to be the double integral over that region of the constant function 1. So the trick is that we have to figure out correctly what the bounds of integration are going to be for this region. And you always want to remember the rule of thumb to start with the outermost bound first. In this case, we'll start with x, and then move to the innermost bound y. Well, the outermost bound x is going from this x value right here, which is negative r, to this x value right here, which is positive r. So very often, figuring out the x bounds is very, very straightforward. You can almost look at a picture sometimes and tell what the correct x bounds of integration is going to be. So x, right, is between negative r and r. Y, on the other hand, is not so straightforward because of the fact that for any given x value, if you fix an x value in this region, the lower bound for x is this, the bottom of the circle, and the upper bound for the lower bound for y is the bottom of the circle, and the upper bound for y is the top of the circle. And this changes depending on what point you look at, right? If we look at this point right here, it's going to have a different lower bound and a different upper bound than this point right here. So we have to include that in the bounds of integration for y when we figure this out. So what this means is that we have to figure out exactly how y depends on x for the upper and lower part of this boundary. And that comes directly from the equation of the circle, which is that x squared plus y squared is equal to r squared, which give us the equation r squared, or y squared is equal to r squared minus x squared, or y is equal to plus or minus the square root of r squared minus x squared. So for x between negative r and r, y is between positive the square root of r squared minus x squared and negative the square root of r squared minus x squared. And so our boundary for y here is going to be negative square root of r squared minus x squared to positive square root of r squared minus x squared. And you see that the upper and lower bound for a non-rectangular region in general will have to be a function. Right? In general, you're going from the lower bound as a function of your first variable to an upper bound which is also a function of your first variable. But this is the correct way of doing this, and you always have to do this for a non-rectangular region. And this is why Fubini's theorem, which we'll talk about next lecture, is simple to state for rectangular regions, but sometimes can be very difficult for non-rectangular regions. So negative r to r, the antiderivative of 1 is just the function y. We have to evaluate this at the upper bound and the lower bound. So r, or y evaluated at this upper bound, is the square root of r squared minus x squared, and minus y evaluated at the lower bound, it'll be negative square root of r squared minus x squared. So the integral that we have to evaluate is the integral from negative r to r of 2 times the square root of r squared minus x squared. And this integral we can evaluate directly using the method from Calc 2 of trigonometric substitution. Specifically, we'll substitute in x is equal to r cosine theta, which means that dx is equal to negative r sine theta d theta. So this integral becomes the integral of the square root of r squared minus x squared, which in terms of theta is r squared cosine squared theta, and then dx is negative r sine theta d theta. And we also have new bounds from the trigonometric substitution. Our initial bound, or top bound here, is r, so when x is equal to r, you get the equation r is equal to r cosine theta, or cosine theta is equal to 1, which means that theta is equal to 0. And from a similar calculation, when x is equal to negative r, you get theta is equal to pi, because that means cosine theta is equal to negative 1. So the new bounds in this trig substitution are going to be from pi to 0. And then here we can factor out an r squared under the square root. The square root of r squared, so we'll write this down, this will be 2 times, we'll move this over a little bit so we have a little bit more space. That's going to be a negative sign, it's negative 2 times the integral from pi to 0 of the square root of r squared times the square root of 1 minus cosine squared of theta times sine of theta d theta times r, because there's an r right here as well. So the square root of r squared is just equal to r. we can also do this nice thing where you have a negative sign here, and whenever you multiply a definite integral by a negative number, the order of integration switches and the negative sign goes away. So this becomes 2 times r squared times the integral from 0 to pi of the square root of 1 minus cosine squared, which is sine squared, times sine of theta d theta. And then the last argument here is that sine of theta is positive when theta is between pi and 0. And so therefore this square root of sine squared theta is just equal to sine of theta. So square root of sine squared when sine of theta is positive is just going to be sine of theta. So it's sine of theta times sine of theta, or sine squared theta. And this becomes a nice trigonometric integral that we can go through and calculate. To calculate it, we use what's called the half angle identity, or half angle formula from trigonometry, which says that sine squared of theta, or it's that double angle formula, is equal to 1 minus sine of 2 theta over 2. So this integral becomes 2 r squared times the integral from 0 to pi of 1 minus sine of 2 theta over 2. 2 times 1/2 is just 1. This is r squared times the integral from 0 to pi of 1 minus sine of 2 theta